Let's start today. I owe you one more very, very important random graph model that has been crucial in understanding the evolution of networks. It's one of the first models that was able to do so, and it's still quite popular to this date, has very nice properties, and has been generalized in various ways. And that's the Alberto Bravasti model. As I said, originally the model was intended to try to explain whether the internet was robust and whether, taking a few edges or a few nodes out would be enough to sort of destroy the connectivity. In reality, this model does not do very well in predicting that specific aspect of the internet. More than anything is because the internet as it exists today has a really high clustering coefficient. It's very redundant, let's say. It has too many pathways that can get you from one place to another. So even if you take down the main servers out there in the world, you're not going to destroy the connectivity of the universe. So in that sense, this model is not great for predicting what it was originally intended for. However, it's still a very important model to try to understand and to propose the mechanisms that lead to having scale-free graphs. Why? Because it explains something about why is it that when we're looking at social networks, as I said before, to me, a social network is anything where the edges and the vertices are being decided by humans, not by other things that don't have choices. So the internet would be a social network in my mind because humans decide where to put servers, who to connect them to. The web graph would definitely be a social network in the sense that I create a website and I decide how to link it to the existing web. So in that sense, what's important about these models is that it tells us why is it that we see what we see in terms of certain nodes, certain web pages accumulating a lot of importance just because they're already important, right? Like once they become important enough, they tend to attract a lot of attention. And that's what these kind of preferential attachment family of models do. So this is an evolving model in the sense that we have a graph where we're assuming that we start at the beginning with either one vertex if you want, or maybe a small graph of some shape. And once we have that, we start adding new vertices one at a time. And each new vertex is going to come and choose to attach to the existing graph in some way. There are many variations of this, and I will cover one of them at least in a few minutes. But let's start with the simplest setting where you have one vertex has one edge. It comes in and is going to choose where to attach itself to. And if you think about this one vertex being a person, then you would say, and the network being Facebook, you would say, well, if I'm going to join somebody who, by befriending that person, who am I going to pick? Well, I probably am going to pick somebody that is already very popular, somebody I know of because that person is popular. And if I do that, I'm using a preference rule in order to attach to that vertex. So vertices that are already very important to the network will tend to attract more and more and more vertices as the new ones start coming in. So this model, as I said, is due to Albert and Bravasti, and it was written originally in the context of physics. The two of them are physicists, and then it was later mathematically studied by Boloas and Riordan. And it's still, to this day, this one and many of its cousins are still very, very important. In general, we call these kinds of models preferential attachment models because the idea is a vertex comes in and it has a preference. And that preference in these models is dependent on the degree of the vertices that are already in the graph. So for the original Albert Bravasti model, what we have is a preference rule that says that as each vertex arrives, it's going to draw an edge, one edge, and it can do so. It can attach to itself, just create a loop and basically just say, I'm here, but I'm not connecting to anybody. Or it will choose that edge to connect to one of the existing vertices in the graph. And the way it does so is that if I am the kth vertex to arrive, then I will choose to attach to vertex I, somebody who is already there, with a probability proportional to the degree of that vertex. So if vertex I has 100 friends already, then, and there's 1,000 nodes in the graph, then I will attach to that vertex I with probability 100 over 1,000. So as you can see, the bigger the degree, the more likely it is I am attached to that. This term over here just corresponds to the probability of creating a self loop. And what's very important when this model came out is that it was a model that could predict why is it that we see scale-free graphs pretty much everywhere. Almost any social network will look like a scale-free graph in the sense that its degrees do not decay fast. They tend to have pretty heavy tails. This one is a Pareto tail with index 3, which means that it actually has infinite variance. So it has finite mean, but infinite variance is very heavy. And as I explained earlier in this course, when we have this kind of scale-free graphs, what we're going to see is that although most vertices have a typical degree close to whatever the average of the graph is, you're going to have some really, really large vertices that have way bigger degrees. And the proportion of those big ones decays as a power law. Okay. So how can you generalize this model? Well, one of the problems that the original Alberto Bravasti model had is that you can only produce power laws of index 3, or in the tail version, index 2. And well, that was sort of not general enough. One would want to hit something else. For many years, I remember thinking, going through the literature and seeing that back 10 years ago, the web graph used to have a power law of tail index 2.1. So you wanted something, you know, and in the version that I had before, that would be 3.1. So you want something in the middle. And if you're trying to hit it exactly, well, this model can't do that. One way of fixing this model is by allowing each vertex not to bring in just one edge, but to bring, when they arrive, m edges with some m, 2, 3, 4, whatever number you want. In the most simple version of this generalization, we have a fixed number of edges that is the same for all the vertices. And when this new vertex comes in with a corresponding number of edges, then it's going to choose how to attach each of the edges according to the same preference rule as before, which is proportional to the degrees. And we're going to allow one extra parameter, which is going to be this delta, that can provide even further adjustment there in the modeling. So my attachment function is going to be proportional to the degree at the time that I'm attaching the jth edge, plus this delta that can be negative. So the idea of these extra delta is that it allows us more versatility in constructing the power laws. And for this particular model, which is one of the many generalizations that exist on preferential attachment models, what we have is that the degree distribution on the graph, the empirical degree distribution, is indeed a power law, just as before, with some constant of proportionality that now is going to depend both in m and in delta. But what we gain from adding this extra level of generality is now that tail exponent, which before was just 3, exactly 3, now it's 3 plus delta over m. So remember, the delta can be negative. So it goes from 2 to as much as we want via the delta, right? So we can make it a lot thinner by making the delta big, and the heaviest that this goes is the previous case that we had. Actually, this goes a little bit more. This one was 3. So this one can go all the way by setting delta equals to minus m. This can go up to 2. So you can see a small generalization of the model can give you more versatility in the modeling. And the main ideas, the main properties of the model actually remain essentially the same. So one thing to keep in mind when we're looking at preferential attachment models, or in general, any kind of evolving graph, is that the vertices that we're modeling have a timestamp. They have a label, and that label actually tells you a lot of information about who that vertex is. Let's say that we start the graph with one vertex, where vertex 1 is the oldest vertex, right? And because it's been there longer, it's going to have a lot more time to actually create a lot of connections. And because it's been there also longer, it's going to have a bigger degree, which is going to attract connections even faster in the future. So older vertices tend to behave very differently from younger ones. So a young vertex could arrive right now and it just comes in with either 1 or m edges, but its degree is just going to be m or m plus 1, and a directed graph, it could be just 1, for example. So these are small vertices with small degrees. So the young ones are are really very different from the big ones. And to give you an idea of how different they are, the young vertices, the ones that are closer to the fringe of the process, are going to have degrees that look reasonably stable and not very large, of order 1. Whereas the largest degree, which tends to be very close to the beginning of the formation of the graph, is growing at a rate of n to a certain power over here, which is inversely proportional to the one we saw before. So these are growing very, very fast. So the older vertices look very different. And because of that, analyzing this kind of graphs actually is rather different than analyzing the static models that we talked about last week. Just to give you an idea, this is one of the graphs that we simulated. Jose made this one. It's a preferential attachment graph. It's an Alberto Bravasti graph. And because we allowed the vertices, new vertices, to come in and sort of create a self loop with themselves and not connect to anybody, this particular realization I like because it has 2 components. Here's one component, and here's another one. So it's a disconnected graph just out of pure chance. And you can see that the older vertices, if I'm not mistaken, I want to say that this one is vertex 1 and this one is vertex, also, what's the number? I don't remember, 10. You can see the label there. So the older vertices, you can see they have more higher degrees, they have more neighbors. This one has even more neighbors. So my guess is that if this graph continues growing, maybe, there's a chance that this vertex will become the bigger one, even overpowering the oldest one, but they're still in the order the first few top vertices, right? These are the oldest vertices, whereas some of the newer vertices, let's say this one, this 80 right here, has only one edge and nobody else is connecting to it. So things on the outside, on the fringe, tend to be very small, whereas the older ones tend to form these sort of clusters of very large degree nodes, and in general, more edges altogether. So this is typical of a graph where we can keep track of the evolution, just because at the biggest level, at the broadest view, the graphs are always growing. And, at a fine scale, somebody might drop from Facebook, cancel their account, somebody might stop subscribing to Twitter. But in the macro scale, these things are always growing. So the more people come in, the more they feed into these preferential attachment rules, and the more they make the old vertices bigger and bigger. If you have any questions, please let me know. This is the last of the models that I wanted to tell you about. So now we've seen a fair number of them. I have a little summary in a second. So if you have questions about the model, I think this is a great time to ask. Otherwise, I'm going to give you a super crash course on how to simulate these graphs. So if you've never seen any of these before, hopefully this is just the bare minimum that you need to do so. So if you have questions, please do so. Ask them right now. Otherwise, this sort of changes the topic a bit. Ready? Okay. So here we go. You might be wondering how exactly we got those graphs that I've been showing, right? How do you generate them? You might want to just take a look at one of them and see how they look different from one model to another. You might want to do experiments with them. You want to play with the parameters, make some parameters bigger, some parameters smaller. You might look at properties and think like, hey, maybe there's something that is true for large graphs, but not small graphs. So you might want to create a whole sequence of these graphs where the number of vertices keeps growing and growing, and try it at different sizes. Or you might actually have some interesting process that is operating on a graph. You might be looking at opinion dynamics, where the graph is representing people and how they talk to each other. You might be looking at an epidemic that is moving through the graph or something. So you want to actually do something else with the graph, but the graph is an important element of your model. And you want to make sure that you can generate a graph that at least mimics some of the important properties of the real problem you're studying. So regardless of what your reason for wanting to do this is, it's a good idea to know how to do it and how to use simple tools like your favorite programming language to accomplish that. So I'm going to try to tell you a bit today of what are the steps that you would need to follow in order to generate any of the graphs that we've talked about throughout the first couple of weeks. So the question that I posed to you is like, do you have any ideas of how you would generate a graph? Anybody? No? You can put something on the chat if you have any ideas of how you would do so. Okay, no volunteers.
Maybe I would take like, well, for example, for the Erdős-Renyi type of graph, you could make a set of all the possible joints, vertices. I'm sorry.
Yeah.
We'll just go and, well, you can generate sometimes random numbers with Python and just give a fair coin throw for each one. And then you should get a subset of all the connections generated. Then you should be able to plot that into a graph, but I don't really know how I would do that.
Well, that's awesome. You just gave us the algorithm for generating Erdős-Renyi graphs right there. And I want to take that to the next step and show you not only the Erdős-Renyi, but all of the models that we have here based on that idea. So thank you. That was actually a really good, good answer to my question that I posed. And what you described is something we call stochastic simulation. And stochastic simulation just basically is the idea of using random numbers, and any computer can generate random numbers to recreate the graph based on the rules that we've determined in each of the models. So if what we want to do with our graph is to play with all that, what we would do is we would try to write a little piece of code, a program, using your favorite programming language, and use this idea of stochastic simulation, which is based on getting random numbers from a computer to recreate the randomness of the real world, right? Once we have that randomness, then we can transform that into coin flips or into other uniform choices or proportional choices as we see fit. And that's what I want to talk about today. Let's start with uniform numbers. So this is the most essential, it's basics element of any stochastic simulation problem. Any programming language that you want to pick, Python, R, C, MATLAB, anyone, will actually have the capability of creating random numbers. Now, computers usually create only one kind of random numbers, and that's going to be uniform numbers in the interval 0, 1. Technically speaking, I won't go into the details of that. What it's generating is a little bit something that is just close to that, but that for the purpose of statistical analysis, they pass all the tests that we need them to pass. Even Excel. So if you don't like to program, I've generated graphs even with my basic Excel. You don't even need something like Python, C, R, or MATLAB to do it. I won't go into doing it with Excel because it is extraordinarily inefficient to do so, but it is possible using this idea of coin flips. So as I said, everything boils down to generating one kind of numbers, and that's a uniform between 0 and 1. This is, from our point of view, something that looks uniform on the continuous interval, so that every single value on the continuous interval 0, 1 can be taken with, let's say it informally, with equal probability. Technically, what I just said is not rigorous because for continuous distributions, any one point cannot be taken with any positive probability. But for any open interval, for any interval of size, let's say b minus a, inside that interval, then the probability that my uniform would lie in that particular interval is going to be equal to the length of the interval. Right? So that's the idea about a uniform. And I guess informally, that means every point inside the interval is equally likely to happen. Okay? Now, what it turns out to be is that that's all you need. There's really nothing that we cannot generate using just uniforms. And as a matter of fact, even the most sophisticated simulation programs, what they're doing at the core is using the uniform numbers to generate anything else that you want. If you've ever played with these kind of ideas before, you might find that some programs have specific algorithms for specific distributions. Most of them are based on just the uniforms alone, and with maybe sometimes the exception of the normal, where sometimes there's more efficient ways of doing so, that where the one-to-one relationship with the uniform is not so obvious. So we have a whole set of techniques to generate any kind of randomness based just on these guys. Numbers that are randomly chosen on the interval 0 to 1 with uniform probability. Let's start with the first of our random variables that we're going to generate, which is the coin flip. A coin flip, in Spanish, we would say it falls cara o cruz. In Mexico in particular, we would probably say águila o sol. And I'm curious to hear what is the corresponding coin flip terminology in other countries outside of Mexico. Anybody wants to volunteer one? Cara o seca in Argentina. Oh, that's cool. Any other one? Seca. Anybody? Cara o coroa. Well, if you put them on the chat as we go, I'm very curious because I never know how to translate these things. As I said, I think that the águila sol is very much a Mexican thing. And if you ever wonder why, all the coins in the Mexican currency, the peso, they all have an eagle on the back. And the sol, I have no idea where that comes from. I think it's some coin that existed a long time ago, but these days they're mostly faces, right? Faces of famous people in Mexico. In any case, whatever you want to call them in English, we call them head or tails. And I'm still not sure what that is either. That makes no sense to me either, but whatever. As far as I can see in the dollar, we have something on the back that is not a tail, but it has two possibilities either way. It lands on one side on the head or on the other side on the tail. Now, for most of our coins, our coins are created in such a way that they're roughly equally likely to fall on one side than the other. So they're fair coins in the sense that the probability of landing heads is 1/2 and the probability of landing tails is 1/2. For the purposes of what we're going to be doing here, it's a little bit more convenient to have biased coins that can land heads with whatever probability P that we give them, and with complementary probability 1 minus P will land on the tail. To make this into a random variable, we're gonna associate the value 1 with the head and the value 0 with the tail. So the next question is, if I give you a uniform number generated by your computer, or by Excel, or by whatever you want, that is equally likely to be any number on the continuous interval 0 to 1, how do you get me a coin flip from there? Anybody? Any ideas?
Well, you can just say if it's less than or equal to P.
Yeah, so I'll give you the uniform. And let's say the uniform is 0.773. Was that a head or was that a tail?
Well, it will depend on the value of P, right? Or like.
Okay, let's say that it's fair.
P. Oh, okay, then that would be a tail.
That would be a head, right? So if it was a fair coin, what you just did is you took the interval 0, 1 and you split it into 2. If it's to the right, you give me a head. If it's to the left, you give me a tail, right? So that same idea actually is exactly what we do. There's nothing magical about generating coin flips. I take the interval 0 to 1. I write P somewhere, wherever my P is. If it's fair, I put it in the middle, of course. And I identify the subintervals, the one from 0 to P with the event ahead, and the interval P to 1 with the event to tail. Why? Because the probability of a number, a uniform number landing here is equal to the length of this subinterval, which is P. The complementary probability of landing on this second interval is 1 minus P, which is the length of this interval, right? So now by deciding, well, give me the uniform, map it to this interval, and choose which to give me, you just generated a random coin flip. Sometimes just, because this coincides with some of the other methods that we use, instead of doing the mapping the way that I did it from 0 to P and from P to 1, often we write from 0 to 1 minus P and from 1 minus P to 1. And this is related to some of the things that we're going to be talking about in a few minutes, called the inversion transform method. So the idea being that you want to have the events, the possible values of your random variable in increasing order. So all I did is I now made the interval that has length P, this one over here, to be the second one because it's associated with a larger value of 1, and the interval that has 1 minus P on the left because that's associated with a value of 0. So either of the two are exactly the same. They will give you a different value of X for the 0.773, but they both have the same distribution, and they have the distribution of a coin flip that lands heads with probability P. Any questions about this?
I'm still confused as to how a computer or how we develop an algorithm to generate a random number in the interval 0, 1, or even, yes.
So that varies from one program to another. Do you program in any language?
I know just a bit of Python, but that's it.
Isn't that rand, Jose? I program very little in Python, but I think it's RAND. And
I think that every programming language has like a built-in function that generates a uniform random number. I think that like I don't know if like every, but I think that it's rather likely that every programming language has like a built-in function that allows you to generate random numbers like between 0 and 1. So like,
if I was, yeah, but I do you program in Python, Jose?
no, I haven't used it.
It's rand, yes, that's what I thought. Somebody else already commented that's rand with, in C and Python. It's also rand in MATLAB. It's also rand in R, right? And it's also rand in Excel.
Yeah, I meant how can we build an algorithm? Like, how can we build the rand function in the first place? That's what I'm confused about.
That is an interesting topic. I wasn't planning on going to that. It's actually quite interesting. And I'm happy to take that after the lecture. So if you just stay at the end, I can explain in detail how the pseudo-random number generators are created. And I can explain a little bit about the one that is today the standard for generating uniforms that most programs use. It's something called the Mersenne twister, and it's not obvious what it's doing. But I can explain the basics of how those come into existence at the end. It's a little bit off topic for what I'm going to be doing. So if you wish, I would be more than happy to go over a quick review of how the computer actually generates those. And if you notice in my answer, I use the word pseudo random number, because as I briefly mentioned before, what a computer generates is not really random. It's actually a deterministic function that creates numbers that look random enough. So they're not truly random. They're just designed in such a way that if you run statistical tests on them, most statistical tests will pass and will recognize them as uniform numbers. But that's another discussion, so I'll take that at the end, if that's okay.
That's great, thanks.
Okay, so now we know how to do coin flips. The next step is I'll give you a random variable that takes, let's say, k values, whatever those values are, so a finite number of values with specific probabilities of each one of them. You can make those numbers 1, 2, 3, 4, 5, or you can make them, -7, 2, 17, 113, 113 times pi, whatever the numbers are, as long as there's a finite number of those. This is something we call a discrete random variable. And this over here, the probability of the random variable taking the specific value xi, let's say the probability of x being taking the value, what did I have to say? 117 times pi, is the corresponding probability here on the left. So what I have is a sequence of probabilities, and by that I mean I have k numbers that are all non-negative and that they add to 1. And those indicate how likely it is for the random variable to take each particular value. If I want to generate a sample of this random variable x, what I do is I'm first going to construct the cumulative distribution function, or the CDF. And I'm going to do it here in a discrete sort of syntax by just taking and saying that f of I, which is the probability that x takes a value smaller or equal than the ith value of my sequence, is the sum of the probabilities of everybody smaller than that, right? So all the other values here, because this is discrete, this is just the sum of the probabilities P1, P2, up to Pi. The standard is to always have these in increasing order. They don't have to be in sequence or anything, but the notation usually calls for us defining them in increasing order. So this is the cumulative distribution function of this discrete random variable. So now, just to give you something to think about, let's suppose that I want to simulate a 6-sided fair die. So I want to play Risk, so I need a die with 6 sides, numbered 1, 2, 3, 4, 5, and 6, and I want to simulate my die, but I don't have it. I lost it. It fell under my desk, but I happen to have my computer with me. So how do I simulate the toss of that die using one uniform? Anybody?
So if it takes a value like between 0 and 1/6, it's a 1. Between 1/6 and 2/6, it's a 2, and so on.
Exactly.
It should be like that, right?
So for the 6-sided die, there you go. That's the algorithm. I divide my interval into 6 pieces, and I map each of the pieces to one particular value, right? This comes in handy if you want to simulate 13-sided dice, for example. The algorithm that you just described in its general form is the following. We have a uniform number between 0 and 1 right here. I take the interval 0 to 1, and I'm going to split it according to the cumulative distribution function. Right? So now these are the Fs. These are not the probabilities, they're the cumulative probabilities. Once I have them like this, I'm going to map one particular value to each of those. Notice that this one is happening with priority P1. This one is happening with priority F2 minus F1, which is P2. This one is happening with priority F3 minus F2, which is P3, and so forth. So I can have a one-to-one correspondence between landing here and returning that value. Landing there, return this value, landing here, this value, and so forth. So this is a general version of the method that we just described for both the coin flip and the 6-sided die. Now, this is just a little trick that I'm going to use later in the pseudocode. So I'm going to write it like this. What I'm returning is this correspondence. So if it lands here, you can think of this as a case statement where it says, if it lands here, return this. If it lands there, return that. If it lands here, return this. However, it's sometimes a little bit easier, especially when you're programming, to use these indicator functions because those are comparisons that the computer can do fairly easily. And if I write them in terms of the if cases, this is the sum of the indicators that I'm in this interval, in that one. And because these are disjoint, only one of these is going to happen. Sorry, and this is a little typo. I should have put here just F greater than U. I'll fix that for the next one because I am returning the value of K where that landed. So I have a little typo there. I'll correct that, but the idea is you're just taking the cumulative sum of how many are to your left, and that's the value that you're going to return. Jose, you didn't catch that one. Okay. So now that we have an algorithm to generate discrete random variables, I have to show you how to generate one more kind of random variable. That's going to be a continuous distribution. And the reason for that is I want to make sure you have an algorithm for generating scale-free graphs, and that requires generating Paretos. So in order to do that, I'm going to take a random variable and I'm going to assume that it has a cumulative distribution function that is continuous. It's a continuous function and strictly increasing when it's neither 0 or 1. Usually, if it has a bounded support, then it can be 0 to the left of the first value that is going to be non-zero, and it can be 1 at some point later. So if you think of a number that can take values between 7 and 15, then up to 7 is going to be 0, and after 15 it's going to be 1. So that's fine, but in the middle I need it to be strictly increasing for this method to be well defined. And more importantly, we're going to assume that this distribution function has an inverse. And you can see where the strict increasing part comes in handy, because if it wasn't strictly increasing, then the inverse is not well defined, at least not like this. There's ways to fix it, of course, but I'm not going to go into those today. The algorithm consists in first we generate the uniform in 0, 1, and then I simply return x to be the inverse function evaluated at the uniform. And this is going to have the property that this random variable that I just generated, x, has distribution f. This is a really nice sort of algorithm called the inverse transform method. So here's one example, the one that I'm going to use later. So I want to be able to generate from the Pareto distribution. The Pareto distribution has the form 1 minus x over b to the minus alpha, where alpha is positive, b is positive. The support of a Pareto is anything bigger than b. So it's always non-negative, but it doesn't take the values between 0 and b. This parameter alpha, it's called the shape parameter, and it tells us how thick the tail distribution is. So it controls that. And the b parameter is called the scale. So it helps us control the support and also how big or small it is. So you can think of the scale just multiplies the random variable by something or makes it smaller by something that whatever this value is. Now, if I want to compute the inverse of this, so I'm going to do u equals 1 minus x over b to the minus alpha. And then I'm going to try to solve for for x. So now I have x over b to the minus alpha equals 1 minus u. And I'm going to take the 1 over alpha root of everything. So x over b is equal to 1 minus u to the minus 1 over alpha. And finally, x is equal to b times 1 minus u to the minus 1 over alpha. In other words, the inverse is b 1 minus u to the minus 1 over alpha. So now that I have this, I can generate Paretos by just setting my random variable x to be b times 1 minus a uniform to the minus 1/2. In our code, sometimes instead of using 1 minus u, we just use u because u and 1 minus u have the same distribution. So it makes no difference. So now we have all the elements that we need. That's all that's needed to generate any of the graphs that we've discussed in the course. So the graphs that we have discussed and that Jose is going to show us how to do those are the Erdős-Renyi graph, the Chung-Lu model, the stochastic block model, the random intersection graph, and the Alberto-Bravasti model. In the slides here, and if there's time later to do so after Jose shows you what he's going to show you, I have the pseudocode for generating each of these models. Pseudocode is just sort of the informal rules of what are the steps that you need to follow without using any specific language to do so. So you can just take that idea and translate it into whatever language you want to use to create it. In all the examples, the goal is to generate the adjacency matrix A. So our final product is this matrix, and then depending on which which programming language you're using, there's different functions that allow you to do the visualization of that graph. But it usually reads the edges from this adjacency matrix A. Okay. So I'll let you then take over. Let me close this. And I'll let Jose take over from here. Go ahead. You have to unmute yourself.
First I want to say I'm gonna do the presentation of the simulations in Spanish. So Spanish is coming in 1, 2 now. Las simulaciones que les voy a mostrar en este momento son simulaciones que generé en el lenguaje de programación R. Y me parece que están, o sea, que son como lindas porque es fácil como escribir el código y también te permite hacer como comentarios. Creo que este código va a estar disponible en la página, esperemos. Entonces, hay un par de paquetes que tengo que instalar que esencialmente te permiten visualizar gráficas y hacer como distintos plots. Y la primera gráfica que vamos a estudiar es el modelo de R2-Rangy. Y vamos a hablar del caso homogéneo, ¿no? Entonces, como habíamos platicado, en la gráfica de R2-Rangy, cualquier arista entre dos vértices va a estar dentro de la gráfica con probabilidad P y todas las aristas son independientes las unas de las otras, ¿no? Entonces, el código que necesitamos usar para generar la matriz de adyacencia, vamos a empezar generando la matriz de adyacencia. Entonces, escogemos el número de vértices, en este caso voy a usar 100 vértices. Y vamos a definir C igual a 3 y C representa el grado promedio que tienen los vértices en mi gráfica. En este caso, voy a esperar que el grado promedio de todos de cada vértice sea 3 y la probabilidad de conexión entonces va a ser 3 sobre n, ¿no? Entonces ahora, la matriz de adyacencia, vamos a empezar con una matriz de adyacencia que es una matriz n por n y tiene todas sus entradas 0. Y lo que vamos a hacer es que vamos a ver todas las parejas de vértices I y J y vamos a incluir la arista IJ con probabilidad P. Este código aquí simplemente me está diciendo que con probabilidad P pongo la arista, con probabilidad 1 menos P no incluyo la arista. Entonces vamos a correr esta parte del código. Ya acaba de correr. Y una vez que tenemos eso, podemos generar la visualización. Aquí estoy utilizando el paquete iGraph. Entonces, primero generamos el objeto que contiene la gráfica y hay ciertos como parámetros de visualización que tenemos que estipular. Y pues podemos correr esto. Y si bajamos un poquito, aquí vamos a ver nuestra gráfica R2-Rangy. Con 100 vértices y probabilidad de conexión 0.03, ¿no? Entonces, como podemos ver, como habíamos comentado, la gráfica de R2-Rangy es homogénea, lo cual quiere decir que no hay vértices especiales en esta gráfica y las cosas se ven como relativamente uniformes, ¿no? Ahora, si queremos generar una visualización dinámica, podemos utilizar un paquete diferente. Entonces, este código que está aquí sirve para generar una visualización dinámica. Vamos a ver exactamente la misma gráfica. Y aquí podemos ver cómo, por ejemplo, este vértice que agarré tiene grado 4. Este otro vértice que estoy agarrando aquí tiene grado 3. Este vértice aquí también tiene grado 3 y tiene un amigo aquí de grado 1. Y como podemos ver, la gráfica... bueno, igual no se ve tan bien, pero la gráfica tiene ciclos muy largos. Me gustaría que se viera más claramente. Y otro ejemplo que me gustaría mostrarles, voy a correr otra vez este mismo código, pero en lugar de utilizar el grado de vértice 3, voy a utilizar grado número 1, ¿no? Como vieron, casi todos los vértices en la gráfica estaban conectados. Y lo que nosotros esperaríamos si tenemos grado 1 en promedio es que sí hay una componente conexa como relativamente grande, pero no gigante. Y vamos a ver qué es lo que ocurre. Si lo corremos con grado promedio 1, podemos ver que hay una componente conexa que es relativamente grande y hay un par de componentes conexas más pequeñas, pero muchos de los vértices están completamente desconectados, ¿no? finalmente, si reducimos este grado un poquito más, vamos a reducirlo a grado 0.5. Eso quiere decir que en promedio, el grado promedio de los vértices va a ser menos de 1. Lo que vamos a ver es que la gráfica va a ser casi totalmente desconexa. ¿Ok? Vamos a ver. Entonces podemos ver que aquí las componentes conexas, no hay ninguna componente conexa particularmente grande, casi todo está fraccionado completamente, y eso está de acuerdo o viene de manera consistente con lo que habíamos comentado acerca de las propiedades del R2 ranging, ¿no? Voy a ir un poquito más rápido. Ahora vamos al modelo de R2 ranging no homogéneo, o también el modelo Chung-Lu. En el modelo de Chung-Lu, la probabilidad de conexión depende de un peso, y entre más grande sea el peso, mayor es la cantidad de conexiones que ese vértice va a tener, ¿no? Entonces vamos a empezar generando una matriz con 100 vértices. Vamos a generar una matriz de adyacencia con 10 vértices, 100 vértices. Y para poder generar este modelo necesitamos simular paretos, ¿no? Entonces vamos a utilizar la regla que acabamos de aprender para generar paretos con la inversa. Entonces vamos a generar uniformes entre 0 y 1. Para cada vértice vamos a generar un uniforme entre 0 y 1, y luego vamos a aplicar la transformación inversa de la función de distribución, y después vamos a generar la gráfica, incluyendo las aristas con la probabilidad P que se encuentra con los pesos, ¿vale? Entonces vamos a generar esto. Y vamos a ver cómo se ve esto en la gráfica estática. ¿Ok? Entonces vamos a ir a ver cómo se ve. Y como podemos ver, en este caso decidí colorear los vértices de la gráfica de acuerdo a qué tantas conexiones tienen, donde amarillo significa bajas conexiones, rojo significa más conexiones y negro significa un nivel muy alto de conexiones. Y como pueden ver, la gráfica que tenemos aquí no es homogénea, en el sentido de que hay un par de vértices que tienen grados significativamente más altos que los otros, y hay otros nodos que son como menos conectados, ¿no? Entonces, el behavior, la manera en la que se comportan los vértices, en esta gráfica no es homogéneo y depende de los pesos. Yo me imagino que este vértice aquí tiene un peso muy alto, y también, y también, ¿no? Y si queremos ver una versión dinámica, podemos utilizar otro pedazo de código, y podemos ver aquí, podemos jugar un tantito, hay un par de componentes conexas, y como podemos ver, la cantidad de conexiones de los vértices no es necesariamente uniforme, ¿no? ¿Hay alguna pregunta hasta ahora? O en el chat. Vamos a ver. Ok. Bueno, vamos a continuar. El siguiente modelo que quiero mostrarles, me gusta mucho, es el modelo de Stochastic Block Model. Y solamente para recordarles, en el modelo de Stochastic Block Model, cada vértice pertenece a una comunidad distinta, y la probabilidad de conexión tiende a ser más grande dentro de las comunidades y más pequeña de comunidad a comunidad, ¿ok? Entonces, en este caso vamos a simular este programa está generado en R, que es un lenguaje de programación. ¿Eso responde a tu pregunta? Bueno, entonces lo que vamos a hacer es, vamos a generar una gráfica.
Creo que la pregunta es, what program you're using, ¿no?
El programa que estoy utilizando, RStudio es un programa que te permite como compilar código en R. Entonces el lenguaje de programación es R, y la plataforma en la que estoy haciendo el código se llama RStudio. Lo voy a escribir. R, lenguaje de programación. función R, procesador de texto, R Studio. Muy bien. Gracias por la pregunta. Gracias por la pregunta. Entonces voy a generar 3 comunidades y cada una va a tener 100 vértices, ¿vale? Ahorita vamos a ver una visualización del modelo estocástico para que veas más o menos a qué se refiere, ¿vale? Entonces vamos a tener 3 comunidades, y cada comunidad va a tener 100 vértices, y para determinar la probabilidad de conexión dentro de las comunidades y entre comunidades, vamos a generar algo que llamamos un kernel, ¿ok? Esta matriz kernel me va a dar cuál es la tasa de probabilidad de conexión dentro de una comunidad. Las entradas en la diagonal representan las conexiones dentro de comunidades y las entradas fuera de la diagonal representan la probabilidad de conexión fuera de las diagonales, ¿ok? Entonces, dado que tenemos nuestro kernel que determina la probabilidad de conectividad, vamos a generar nuestra matriz de adyacencia. Entonces empezamos generando la matriz de adyacencia y ahora vamos a ver el modelo de Stochastic Block Model, y en este caso, en lugar de colorear a partir de los grados, vamos a colorear a partir de la clase a la que pertenecen los vértices, ¿vale? Entonces voy a correr esto y lo que vemos es que tenemos 1, 2 y 3 comunidades. Y claramente cada una de las comunidades está muy, muy conectada los unos con los otros dentro de la comunidad, pero la cantidad de conexiones que hay de una comunidad a otra es muy, muy bajo, como pueden ver. Y si queremos observar cómo se ve de manera dinámica, esto me gusta mucho, de hecho. Vamos a ver cómo se ve el modelo dinámico. Podemos ver cómo se repelen las comunidades y se separan de manera natural, ¿no? Entonces aquí podemos ver cómo las comunidades se han separado las unas con las otras, ¿no? Y si queremos podemos agarrar un nodo y podemos moverlo y la comunidad se va a mover toda, ¿no? No sé, me gustan mucho estas visualizaciones, me parecen cool. Alguien pregunta, ¿cómo obtenemos el kernel? Esa es una muy buena pregunta. El kernel es algo que tú puedes decidir. Por ejemplo, yo aquí decidí darle kernel, valor de kernel de comunidad 1 con comunidad 1 de 15, 15 para la comunidad 2, 15 para la comunidad 3, y las probabilidades de conexión entre comunidades de una comunidad a otra las di como 0.2, 0.2, 0.2, ¿vale? ¿Cuál es el valor esperado del grado para vértices en la comunidad, para las comunidades? Creo que tendría que hacer un cálculo, me tomaría un poquito de tiempo, entonces no lo voy a hacer en este momento, pero...
Los grados, José, los grados están calculados en la clase de la semana pasada.
Vale, perfecto. ¿Qué más? ¿Qué significa kernel? Ay, ¿cómo contesto?
Esa es una función de... Este es un conjunto con K comunidades, entonces de K por K al intervalo 0 infinito. Es una función. O sea, para cada par de números, para cada par de comunidades te va a dar un número entre 0 e infinito.
Sí, el kernel simplemente está representando qué tan relacionado está cada comunidad con la otra, y usualmente dentro de las comunidades va a haber un valor más alto en el kernel y de comunidad a comunidad vamos a tener un valor más bajo en el kernel. Entonces es simplemente una función que dadas dos comunidades te da un valor que representa qué tan relacionadas esas dos comunidades están. ¿Eso responde tu pregunta? Vale, ok, perfecto. Ahora vamos a la gráfica con clusters, el modelo de intersección. Habíamos platicado que para el modelo de intersección es necesario simular una gráfica bipartita. Lo puedes pensar, o sea, podemos pensarlo como tener un grupo de actores y tener un grupo de películas y tener decidir cómo los actores actúan en estas películas de manera aleatoria y luego conectar a dos actores si participaron en la misma película, ¿vale? Entonces aquí vamos a generar 100 actores y lo primero que vamos a hacer es generar la gráfica bipartita que corresponde a la relación entre actores y películas. Y luego aquí vamos a generar la matriz de adyacencia que vamos a visualizar, en donde representamos qué actores están conectados de acuerdo a si participaron en la misma película, ¿vale? Entonces generamos esta matriz de adyacencia y si queremos visualizar el modelo de manera estática, vamos a ver, aquí tenemos, como podemos ver, hay algunos actores que no se relacionan con ningún otro actor, y tenemos un nivel de conexión muy, muy alto, y hay algunos vértices que tienen muy alto nivel de conexión, y hay otros que tienen un nivel un poco más bajo. Entonces, lo que vamos a hacer vamos a generar la visualización dinámica, y vamos a ver cómo se ve, ¿no? Ok. Muy bien. Y como podemos ver, no sé si puedan verlo, es un poco complicado porque la gráfica está muy, muy conectada, pero lo que podemos ver es que hay muchas comunidades de grupitos de amigos, entre comillas, ¿no? Por ejemplo, aquí podemos ver un grupo de 1, 2, 3, 4, 5, 6, 7 personas que están casi todas conectadas unas con las otras, ¿no? Aquí podemos ver otro grupo de 1, 2, 3, 4 personas que están todas conectadas las unas con las otras. Y esto es una manera más natural de generar gráficas con redes sociales, porque es muy común que si una persona tiene un grupo de amigos, todas las personas en el grupo sean todas amigos los unos con los otros, ¿no? Entonces este modelo es un modelo un poquito más natural para generar gráficas aleatorias. Que representan redes sociales. Y finalmente, a ver, voy a detenerme como un segundito solamente para ver las preguntas. Ok. Por último, vamos a hablar del modelo de conexión preferencial, y como ya habíamos comentado, en el modelo de conexión preferencial, el primer nodo aparece al inicio y luego los nodos van entrando y conectándose de acuerdo a la popularidad que los nodos que ya estaban en la gráfica tengan, ¿vale? Entonces vamos a generar una gráfica con 100 vértices, y esencialmente aquí en este pedazo de código lo que estamos haciendo es secuencialmente dejando entrar vértices y escogiendo con quién se van a conectar dependiendo de la popularidad de los vértices que ya habían llegado. Entonces vamos a correr esto. Este pedazo de código genera la matriz de adyacencia de la gráfica, y ahora vamos a visualizar cómo esta gráfica se ve de manera estática. Y aquí podemos ver que hay 1, 2, 3, 4 componentes conexas. Y como podemos ver en estas componentes conexas, ¿quiénes son las personas más populares? Pues el vértice 1 claramente es muy popular, el vértice 5 es muy popular, el vértice 4, y todos estos vértices son claramente vértices como tempranos, ¿no? Hay otros vértices que también tienen un tantito de popularidad, como este 40 o el 19, ¿no? Pero los vértices que parecieran ser los más populares son los que llegan más temprano, ¿no? Entonces, creo que hay otra pregunta. Sí, el 41 así, forever alone, ¿no? Bueno, y si queremos ver la visualización dinámica, podemos generarla y vamos a ver. Podemos ver cómo se separan las unas con las otras. Aquí tenemos como el componente más grande. Creo que aquí tenemos otro componente, ¿no? Y lo podemos mover. Este componente está pegado. Y de nuevo, o sea, como ya habíamos comentado, el vértice 1 parece ser muy popular, el vértice 4 es muy popular, y el vértice, estas simulaciones están generadas de tal manera que los vértices se repelen para que se vea bien, y el vértice 41 se repelió de todos y se fue, ¿no? Entonces ya nunca lo vamos a ver forever alone. Bueno, pues esas son las simulaciones que les quería mostrar. Todas estas simulaciones van a estar disponibles en la página web, esperemos que el día de hoy. Y de hecho hay todo esto no es necesario instalar RStudio para poder ver todo esto. Voy a subir un archivo que se puede ver en el navegador. Déjenles enseño como rápido cómo se va a ver. Que tiene como más o menos la explicación de cada gráfica y que tiene también como los plots para cada gráfica. Entonces, vamos a ver. No sé si lo puedan ver, pero solamente se los quiero mostrar rápido. Ay, bueno, creo que no se generó bien, pero no importa. Pues bueno, esas son todas las simulaciones que les quería mostrar. Si tienen alguna pregunta, pueden compartirla por el chat o pueden compartirla por el micrófono, y si no, pues paso la palabra a Mariana.
¿Alguien tiene alguna pregunta? Bueno, José va a asegurarse de que todos los códigos que hemos estado usando desde que empezamos con las clases estén disponibles. Esperemos que los puedan poner los organizadores en su sitio web para mañana o el viernes. I'm going to go back to English just to finish and give you a few more comments. So on the slides, what I prepared is basically a pseudocode version of the code. So it's not specific to any language, that goes over the same ideas that Jose explained, which are the steps in order to generate the graphs. All of them start by defining or initializing what we call the matrix of adjacency, sometimes the matrix, the vector of weights. That's just because many languages like to know what the size of the final product is before you do it. There's some languages that allow you to do it as you go. Some sort of give you warning signals if you try to do that. So what I have here is just the conceptual idea of what are the force and the loops that are being used and the assignments of the adjacency values. You can go through these at your own leisure. I explained, for example, for the Chunlu model, here is the inverse transform method for generating the weights. And again, you can see that at the beginning, the main thing is I'm just initializing the vectors or the adjacency matrix, just so that the program knows what is the size of what is going to be created at the end. So you can see, as I said, I'm not going to go into detail over this, but if you want sort of a generic approach that does not depend on what language you apply it to, you can take these ideas and just go and read every one of these is a loop or a for. If you prefer to use a while and break the while, it's up to you. It's a loop of some sort, depending on what you want to do. There were some questions in the chat about the stochastic block model in particular. So the stochastic block model takes two parameters: the kernel function, which tells you the chances or the likelihood of connecting. These are not probabilities. The kernel is not between 0 and 1. It's just non-negative. So what it just gives you is sort of general weights of how likely is it to connect from one community to another, right? So that's what this kernel function is doing. As I was explaining on the chat, if you pick in the kernel in such a way that the diagonal terms are big and the off diagonal terms are small, then what that's going to accomplish is that the connections within each community are going to be more than in between different communities. So that separates the communities a lot. Now, the bigger in general, so if I multiply the entire kernel by 10 or by 100, then what I'm doing is I'm just growing the degree of everybody, the expected degree. Now, there's some examples that can be sort of a little bit more pathological, where you can play with the expected degrees. The expected degree technically also uses the size of the communities. So if you want the exact formulas for those, you can find them in the set of slides for lecture number 2. And there you can use those formulas for the expected degree on each community to play with the sizes of the communities. The communities do not have to be the same size. You can have some communities that are small and some that are bigger. So this just gives you the general idea. For the random intersection graph, as Jose was explaining, that requires a two-step procedure. So first we have to generate a bipartite graph using this Pareto weights on the degree distribution of the bipartite graph. And then once we have the bipartite graph, which I'm denoting B for its adjacency matrix, then you can go and do the intersection. And what I had here is a sort of a little trick that I like to use when I'm working, especially with MATLAB, just because MATLAB is a program that is meant to work with matrices and vectors. So it's sort of very good at doing that, is to compute the neighbors using the vectors, the rows of the adjacency matrix. So all the neighbors, for example, of vertex I are going to be the row I of the adjacency matrix in the bipartite graph. All the neighbors for J are going to be the Jth row in the bipartite graph. And then if you take the difference, here's a little trick, then what you get is a 1, a -1, or a 0. If it's a 0, then that means that the two vertices I and J have a neighbor in common in the bipartite graph, right? So here's a trick. You can take the absolute value of this vector component-wise, and then the zeros, if there is a 0, then that means that they are connected in the intersection graph. If there is no 0, that means the absolute value is going to be 1, then that means that they're not connected. So those are just little things that when working with matrices come in handy for getting code that is fairly short. So those are the problems. I fixed the little typo, the typo on the other one was missing an XI. I will make sure that correction is made. I had the same typo replicated in the pseudocode for the Alberto Bravasti model, and what it's missing is the value of the random variable, which is J in this case. So here what we're using is the inverse transform method for computing who is the identity of the vertex that you're attaching to. That's what this little piece of code does. And I'm recursively computing the cumulative distribution function as we go using the degree sequence, as you can see here. That's another trick. This is not, I'm just taking the sum of the degrees. It's not a probability. And then once I'm done with those, you normalize it by dividing by its sum. Again, if you're programming, these are very simple little things that you can do in one line. So intuitively might not make too much sense to do it this way, but from the point of view of programming, it's more efficient to do it this way. So that's what I have for today. If you have any questions, feel free to do so. Otherwise, I'm happy to take questions offline. So I'm going to be, if there's questions about today's lecture, I'll happy to take them on right now. And if not, I'm going to end the session, and then you're welcome to stay, and we can definitely talk about some of the other questions you had before.